Okay, so we will conclude this lecture with an introduction to binary algebraic structures. Now, in its most general sense, a binary algebraic structure consists of two elements, a single underlying set, and a single finitary operation. The word finitary means that the operation takes as an argument a finite number of elements from the set. The most common types are unary operations, in which a single element is mapped to a single element in the set. That is, the set A, for instance, is mapped into the set A. Another type is called binary operation, in which an ordered pair of elements is mapped into a single element. For instance, a function mapping A cross A into itself. And then there is a ternary operation, which maps an ordered triple into a single element. And so again, as a function, it is a map from A cross A cross A back into itself. Now, our focus will be on binary operations. Now, as a counterexample to demonstrate a structure that is not a binary algebraic structure, let's consider a vector space. Now, we have not yet formally defined a vector space, but we have looked at vector spaces enough to realize that the vector space consists of two sets, a set of vectors and a set of scalars. And it also consists of two operations, vector addition and scalar multiplication. Now, a vector space requires additional properties, especially of the operations, but at a minimum, there are four elements that are necessary to define a vector space. And so a vector space is not a binary algebraic structure. Now, as I said, we will be focusing on binary operations. So let's define what that is. A binary operation which we generically denote with the symbol star, is a function, well, binary operation star, on a set A is a function which will denote phi, mapping ordered pairs of the set back into itself. Now, an important property of a binary operation is the property of closure. Closure is implied in the definition of a binary operation, but let's define closure. So let the operation star be a binary operation defined on a set on set A. The operation is closed over the set A if, for every two elements, A and B, in the set A star B is also in the set A. We also say that the set A is closed under the operation star. So as a counterexample, let the set A be the set consisting of two elements, 0 and 1, with ordinary addition. Then 0 plus 0 is 0, which is in the set A. 0 plus 1 is the same as 1 plus 0, which is 1, which is also in the set A. But 1 plus 1 is 2, and this is not in the set A. And so the operation of addition is not closed over the set A, and so the operation of addition is not a binary operation defined on the set A. Now, the most general or basic binary algebraic structure that we will study is called a magma. A binary algebraic structure consisting of a single underlying set and we'll call that set S, together with a single binary operation closed over the set S is called a magma. Notice that we are insisting that the operation be a binary operation. A magma is denoted with angular brackets as a pair consisting of the set S together with the binary operation defined on the set S. And again, we use the generic symbol star as a placeholder for a given operation. So in order to demonstrate that a given set together with an operation is a magma, we must demonstrate that the set is closed under that operation. So we'll look at several examples. Let Z1 and Z2 be complex numbers. Then, as we have demonstrated in previous lectures, the sum of two complex numbers is always a complex number. And so the structure consisting of the set of complex numbers together with normal addition is a magma. Another example. Once again, let Z1 and Z2 be complex numbers. Then, as we have demonstrated previously, the product of Z1 and Z2 is also a complex number. And so the structure consisting of the complex numbers together with multiplication, which we'll denote with a dot, is a magma. Now let Z1 and Z2 be complex numbers on the unit circle. Then Z1 is of the form the modulus of Z1 times e to the power of I theta 1, which, because it is on the unit circle, the modulus is 1, and so it is simply e to the power of I times theta 1. And Z sub 2 is equal to e to the power of I times theta 2. And so the product, Z1, Z2, is e to the power of I theta 1 times e to the power of I theta 2, which is e to the power of I times the sum theta 1 plus theta 2, where the modulus of the product, Z1, Z2, is 1. And so the product, Z1, Z2, is in the set of elements on the unit circle, or are on. The product is on the unit circle. And so the structure consisting of the unit circle on the complex plane, together with multiplication, is a magma. Another example. Let theta 1 and theta 2 be elements in the half open interval from 0 inclusive to 2 pi. Then theta 1 plus theta 2 modulo 2 pi is also in the half open interval from 0 to 2 pi, as we have demonstrated previously. And so the structure consisting of the set, which is the half open interval from 0 inclusive to 2 pi, and addition modulo 2 pi, is a magma. Right? Next example. Let Z1 and Z2 be in the set of the nth roots of unity. Then, as we demonstrated in this lecture, the product of those two elements is once again an nth root of unity. And so the structure consisting of the n distinct nth roots of unity, together with multiplication, is a magma. And the final example that we'll look at today, let A and B be elements of the set of integers modulo n. Then, as we have seen previously, the sum modulo n, a plus b modulo n, is once again an integer modulo n. And so the set consisting of the set of integers modulo n, together with addition modulo n, is a magma. Now, in the next lecture, we will continue looking at specific types of magmas, building to what is known as a group. And we will also look at the idea of algebraic equivalence via a very special function known as an isomorphism. and in which we'll be able to demonstrate that two given structures are algebraically equivalent. In particular, we will see that the set of elements on the unit circle in the complex plane, together with multiplication, is algebraically equivalent to addition modulo 2n on the set of elements in the half-open interval from 0 to 2 pi. We will also see that the set of nth roots of unity, together with multiplication, is algebraically equivalent to addition modulo n on the set of integers modulo n. So we'll end here for today. I hope you have enjoyed the 8th lecture. Thanks for watching.